Okay, welcome back everyone. Second talk of the afternoon, and Igor Wigman came all the way from King's College London. So, from there,
Thank you very much. Thanks very much for organizing this wonderful thematic semester. And thanks for inviting me to give this talk. This is based on mainly two papers. One is joined with Zev Rudnik and Nadav Yesha, and a more recent one with Alexander Pushnitsky, who is a gentleman here. I'm sure everybody knows. As I noticed also, yeah. Okay, let me take care. So part one, motivation, and I'm going to define what is Robin Neumann or RN gaps. So let's very general setup. M is a Riemann surface that is two-dimensional manifold. And we're going to mainly discuss the planar situation. So this is going to be a planar domain with a smooth boundary. And we're interested in the Laplace spectrum. And Laplace is the usual operator, capital delta. And Laplace spectrum is basically all the lambda that resolve this Helmholtz equation that is written on the third row. In order to have a complete system, we need to impose some boundary conditions. The most acceptable boundary conditions are the Neumann, that is the normal derivative at the boundary vanishes identically, and the normal derivative is designated here. Forgive me my poor drawing. And Dirichlet is, instead of the normal derivative vanishing, the function vanishes at the boundary. But there is also the Robin or mixed condition, so we choose sigma. Let's think of sigma as just, say, a positive number. So we take this linear combination of the values at the boundary plus the values of the normal derivative of the boundary with sigma multiplying the Dirichlet part. It has to vanish at the boundary. And we think about it, so for sigma equals to 0, this is precisely the Neumann boundary condition. And for sigma, say a number, any positive number, we think about it as a small perturbation of the Neumann operator. But in fact, sigma doesn't even have to be a number. It could be any function on the boundary. And we can think about it still in the same way as a small perturbation of the Neumann Laplace operator. So at this part, we're going to assume that sigma is fixed and is a constant. It's not a function. And sigma equals to 0 corresponds to Neumann, and sigma equals to infinity corresponds to the Dirichlet boundary condition. And we're interested in the Robin spectrum of capital delta, and we order it is well known that this is purely discrete spectrum consisting of eigenvalues. We order the eigenvalues in non-decreasing order. Sometimes there are some spectral degeneracies, but generically there are not going to be any, so this is might be even strictly increasing. And the fact is that if we fix any j and look at lambda j of sigma as a function of sigma, then it is strictly increasing as a function of sigma. The technique to prove it is called the Neumann to Dirichlet bracketing. And then whatever sigma is, we have the while law, which does not fill the Robin boundary condition. It is the first term here is the same no matter what is sigma. It is so lambda j, the number of eigenvalues small or equal than lambda, is asymptotic to lambda times this explicit constant area divided by 4 pi. And it doesn't matter what is sigma. So the first term of while law does not fill. If we are going to be quite lucky, and I'm going to get to the very last slide of this presentation, which based on my past experience is highly unlikely, then I'm going to discuss a little bit, more precise. Sorry? But knowing the chairman, I think it is highly unlikely. Knowing what the chairman told me before this talk, it is even less likely. But let's go back to, okay, so So maybe we'll get to some more precise version of the while law, second term, remainder. But for now, let's stick to the while law. We can define the so-called Robin and Neumann gaps or Rn gaps in boldface, which we defined in a paper with Zev Rudnik and Nadav Yesha in 2020. These are just the differences lambda j sigma minus lambda j 0. That is the Robin minus the Neumann case. And they are strictly positive because of the strict increase of lambda j as a function of sigma. Our goal is to study the statistics of Robin-Neumann gaps and some other properties of the Robin spectrum. For example, whether it's in some particular cases it's simple, it's degenerate, highly degenerate, and other properties. So here's some numerical experiments. Let me just explain what we see here. So this is for 4 different planar billiards. The disk, top left is the disk. Bunimovich stadium, rather quarter of the stadium, right top. Mushroom is a mixed chaotic and integrable case, bottom left, right. And the square billiard, which is completely integrable system, this is left bottom. So what we see, the x-axis designates just the number of experiments. Sorry. And the y-axis is just the corresponding Robin-Neumann gap. So here for the disk billiard, we did 2,000 experiments, 200, etc. The red line is the so-called theoretical mean that I'm going to define over the next 3 slides. And the green line is the accumulating average. I think it's called, yeah.
Just to check, for mushroom, you don't have it connected. You don't have the border between half circle and the square. For mushroom, it's connected.
Yes, it is connected, yes. Yeah, and in fact, it's even star-shaped. I'm going to mention it. It's, I mean, okay, since Misha just raised the question of mushroom, just imagine what is the definition of being star-shaped. And if we put a point at the basis, you'll see that this point could serve as center, so it is star-shaped. Okay, so the green line is a cumulative average, and evidently from the 3 pictures that we designated the green line, and the same thing also true for the 4th one, there is a convergence of the moving average towards the theoretical mean. There's another striking fact in all these 4 examples. So there is a lacuna around the origin, so there are no very small Robin-Neumann gaps here. So for example, there is nothing below, there's nothing below this line here, and in some other examples as well. And we have an explanation for that as well. There is a lower bound. Okay, so now I would like to discuss and state some of the main results. But first, let me state something that everybody here knows much better than I do: ergodicity and quantum ergodicity. So M, the billiard mem, is chaotic if the corresponding geodesic flow is ergodic. Sometimes it's called chaotic manifold or billiard, and sometimes it's called an ergodic billiard or manifold. So in this picture, you can see the difference between a chaotic one, which is the Bunimovich stadium, and the non-chaotic one, which is a disk. For chaotic one, a billiard orbit would fill in, it's going to be dense in the stadium, and it's going to be equidistributed in this stadium. But for the disk, no such thing is true. And what Schneermann's theorem states, which was proven by Schneermann, Colin-Davidier, and Zeldich, is that if a billiard is chaotic, then it is quantum chaotic. What is quantum chaotic is that if we take an L2 mass eigenfunctions restricted to a given subdomain of the billiard, then it converges to the area of the billiard for density 1 sequence. Okay, and the question is, now this is not a definition. The definition is far more general than that. In fact, here is the position space, but the definition is about the phase space of pseudo-differential operators, and not just in position. But for the purpose of this discussion, and for me, it's sufficient. And the outstanding question here is that of quantum unique ergodicity. Quantum unique ergodicity is a property that there are no exceptional sequences, and this convergence is true for the full sequence without exceptions. And the exceptional sequences are called scars. And Hassel proved that they exist steady, and steady is a one parameter family which is parameterized by the flat side of the stadium. So Hassel's theorem states that there exists steady with scars, but it does not actually exhibit a single stadium with scars, and it does not imply the violation of this convergence to the area of A, because it is in the phase space. It's at the level of pseudo-differential operators. Okay. So, as it stands now, there is no single counterexample to this statement asterisk, and it would be great to prove it. Now, here's a statement of one principal result of our study about Robin and Neumann gaps. So recall that the Robin and Neumann gaps are the positive numbers dj, lambda j at sigma minus lambda j at 0, the Neumann, so the Robin minus the corresponding Neumann eigenvalue in ordering. So we proved, first of all, that these numbers dj of sigma converge on average to the theoretical mean that we observed in the first picture. And the theoretical mean is, let's imagine that sigma equals to 1 here, is twice the length of the boundary divided by the area of the surface of the billiard. In particular, we can infer that these numbers dj sigma are essentially bounded for density 1 sequence of j. And when I say essentially bounded, what I mean is that if we take any function phi that grows to infinity, then dj of sigma is going to be smaller than phi of j for almost all j. And here's a Markov bound for the exceptional, for the sequence of exceptional eigenvalues. Okay, so the number of those exceptional ones is bounded by n divided phi of n. And the second result is that if we restrict our discussion to chaotic billiards, then not only we have this convergence on average, but we also can have the same convergence to the same number for density 1 sequence of eigenvalues. And we should conflate that with quantum ergodicity. It's similar to quantum ergodicity. There is a question whether or not there are exceptional subsequences in chaotic case. I'm going to mention a list of open questions, and this is going to be one of them. Okay, so let me explain what is this theoretical mean, where it comes from. There is a general principle in perturbation theory, and there are a lot of people here that know this much better than I do. So there is a variation formula for the derivative of lambda j as a function of sigma. There is a subtlety here. So lambda j is not necessarily a smooth function because so there is a way to choose lambda j as a smooth and even analytic function. But then there are some bifurcation points where different analytic curves intersect. And as a result of this intersection, we have a reordering. But we have to decide whether or not we want to stick with the analytic choice or we want to stick with the order choice. If we want the order choice, then there is no analyticity any longer, but there is still analyticity or smoothness safe to a discrete set of those bifurcation points. So we can still apply the fundamental theorem of the calculus. And the derivative in all those points that are not bifurcation points is the integral of the corresponding eigenfunction squared on the boundary. Now let's assume for a sec that there is a mass equidistribution of those eigenfunctions as it is asserted by quantum ergodicity or quantum unique ergodicity. So if there is a mass equidistribution, then on the boundary, this function phi j x squared is supposed to approximate 1 over the area. Why? Because the L2, the total L2 mass of that function is 1. And then if we integrate this 1 over area of M on the boundary, and we get the length of the boundary divided by the area. But that does not account for the factor of 2, because we claim that the theoretical mean is on the top line here is twice the length divided by the area, not once the length divided by the area. And the reason is because this is not a good way to think about the limit eigenfunction as just constant 1 over area. It is oscillatory. And if you think about it, then that accounts for the factor 2. Okay, so you need, if it is going to be something, let's say sine x, sine y with frequency m at the boundary, then in order to make it weight, in order to make L2 norm 1, we have to factor it by factor 2, and then we get the correct factor. Okay. Now, other than the convergence, we also discussed upper and lower bound. What can we prove about the upper and lower bound? So we have the following general upper bound that is valid for more or less all smooth domains, smooth billiards, is that dj of sigma is smaller or equal than j to 1/3 times some constants. And we can use the y law to translate it as a function of, to express it as a function of lambda j, which is lambda j, the corresponding Neumann eigenvalue, to the power 1/3 times sigma. For the particular case of the disk billiard, we can improve very slightly the exponent of 1/3 by using some lattice point techniques and number theory. So delta, the improvement delta is 1 over 990, and this is what I alluded in the very first slide. We basically use the the more precise version of the while asymptotics, which is valid only for the disk billiard with the particular remainder term. We proved that the Robin and Neumann gaps are bounded for the particular rectangles, and the spectrum is simple for the square. When I say simple here, it's a little bit misleading. Every eigenvalue appears precisely twice because there is some symmetry. But other than that, this is simple. And we also we also studied the spectrum as a function of the aspect ratio, and it turned out that it is very sensitive to some arithmetic properties of the aspect ratio, such as the Diophantine properties, rationality measure, etc. We showed that for the hemisphere, these numbers are in fact unbounded, Robin Neumann gaps. The hemisphere is not a planar domain, but it's still a surface, and we can still study the same problem. I'm going to discuss it in more detail in the second part of my talk. And in fact, they can grow as large as lambda j at 0 to the power 1/4. So this is rather rapid growth. For the lower bound, we assume that the surface is star-shaped. The planar domain is star-shaped. For example, it could be the mushroom, or it could be shaped like that. And we prove that in this case there is some lower bound C that depends, of course, on the surface, on the billiard and the number sigma. There is a very large gap between the lower and upper bound. The lower bound is some constant, and the upper bound is the Neumann eigenvalue to the power 1/3. That's the state of art at this point. There is nothing general that we can prove, that we can improve. Okay. So here are some open questions. So we believe that the star-shaped constraint is just artifact, is just a byproduct of our techniques, and I think it should be removed, this condition. So here's an outstanding question. Number 1, do exist planar domains that the corresponding Robin Neumann gaps are unbounded? So we have the unboundedness of Robin Neumann gaps for the hemisphere, but this is not a planar domain. Okay, and a natural candidate for such unbounded Robin Neumann gaps would be the disk billiard. We've seen some numerics for the disk billiard in the very first picture, and seemingly it's not bounded. And we have another argument. Basically, the whispering gallery mode attains a very large growth for this derivative. And I'm going to discuss it in the third part of my talk if I get there. Yeah.
But the question that what if you take the Buminovich stadium
Yes.
as another parameter instead of just the sigma, but also the width of that? Would you be able to prove something for almost every billiard on that, adapting the Hasselbalch?
That's the third question, which is not depicted here. So yes, we do believe that there are so-called RN scars for the Buminovich stadium. This seems extremely difficult. I'm going to say something, but this is, I agree, this is a natural candidate to show exceptional behavior, yes. Not necessarily unboundedness, but I think that there exists, so probably the correct statement is that for the flat side sufficiently small, there exists a Robin parameter, and there exists a subsequence that converges to a different number than the theoretical mean. I think that's a correct statement, but I would like to challenge anybody to prove it. And the techniques of Hassel are completely unrelated, like they're completely irrelevant. They give nothing, basically, because his result is pertaining only to the momenta. Whereas we need, for the variational derivative, we need the position. Okay, so in fact, I said that's question number 3. That was actually, no, question number 3 is a different one. That's question number 2 precisely. So do there exist RN scars, that is exceptional sequences and parameter and exceptional sequences, so that there are some other partial limits than the theoretical mean? And this is very similar to the question of quantum ergodicity versus quantum unique ergodicity. And for that reason, we call these sequences Robin Neumann scars. And indeed, Buminovich stadium is a natural candidate to show that. So thanks for the question. Okay, so this is the conclusion of part 1. Now part 2, I'm going to discuss the particular case of hemisphere, which is, any questions so far? Okay. So hemisphere. So first of all, let's consider the Neumann, the corresponding Neumann problem. And before we consider the Neumann problem, let's first of all recall the situation on the whole sphere. So on the whole sphere, the spectrum is parameterized by natural numbers L. The eigenvalues are L times L plus 1. And there is a multiplicity 2L plus 1 for every L. And given L, there exists a canonical basis called YLM. This is called the Wiener orthonormal basis for degree L spherical harmonics, YLM. And the fact is that if we look at YLM alone, then YLM, so now let's look at the hemisphere as just half the sphere. And the boundary conditions are going to be end out at the equator, which is the boundary of the hemisphere. So the fact is that YLM satisfies the Neumann condition if and only if M is equal to L modulo 2. And otherwise, that is, if they are not equal modulo 2, this is the Dirichlet. It satisfies Dirichlet on the boundary, it is the equator. What is the Neumann eigenfunctions? These are precisely YLM. These are precisely spanned by YLM for M minus L plus 2, etc., until we get to L. There are precisely L plus 1 of these. And the remaining ones, and they are precisely L, Dirichlet ones. Okay, and just sanity test, L plus 1 plus L equals to 2L plus 1. So we span the entire space. And now for sigma that is constant, it's not a function on the equator, but it's a constant. There is a separation of variable. And we can define the Robin spectrum. So these are, instead of L times L plus 1, these are going to be nu times nu plus 1. And these are going to be corresponding to perturbation of YLM. And we can parameterize them again with nu LM, where M is equal to L modulo 2. And the corresponding eigenvalues are nu times nu plus 1. The fact is that for every sigma positive, this nu LM is going to be a number between L and L plus 1. Obviously, it's not going to be integer any longer. At 0, this is going to correspond to Neumann, that is going to be equal to L. And at infinity, it's going to converge, strictly increase to L plus 1. And something quite interesting here. So as sigma goes to infinity, the L becomes L plus 1. The parity condition that L is equal to M modulo 2 is precisely violated. But then it's going to become equal modulo 2, not to L, but to L plus 1. And this is going to be the corresponding to the Dirichlet of the next cluster. Okay, but here everything breaks into clusters. There is a systematic doubling. Nu L minus M equals to nu LM as a function of sigma, not just for 0, but for every sigma. These are two functions. This is called systematic doubling. Every eigenvalue appears twice, except when M equals to 0. But M equals to 0, there are very few of them asymptotically as L goes to infinity. And this is a typical graph like that. So here L equals to 10. And I only took M that are positive between 0 and 10, and they are equal to 2 modulo L. To L modulo 2. Okay, and the corresponding Robin-Neumann gaps is precisely the number lambda minus the corresponding Neumann, which is L times L plus 1. So what we prove with Zev in the earlier paper is the following. First, that the spectrum is simple, save for the systematic doubling. So for every sigma, all of these are generally different. And also that the Robin-Neumann gaps admit the following limiting distribution, density, as L goes to infinity. So here we take sigma equals to 1, but it's similar to scale any sigma. So the density, I'm hiding some constants here that normalize it to be a probability density function. But this is the density and this is the graph. Notice that here it does not go to infinity at 0, but at the value 4 over pi, but in a convergent way. And there is nothing between 0 and 4 over pi. This is the lacuna that we've seen in the very first picture. And from this point on, I'm going to assume that 4 over pi equals to 1. I'm going to show some results, and I'm not going to be entirely honest about all the constants, and in particular 4 over pi. So pi is going to be equal to 4. But I hope that everybody is going to forgive me. This system admits separation of variables, and there is a circular equation in terms of special Bessel functions for this number nu Lm, and that allows us to derive these results. So here's problem number 3. So let's suppose that sigma is no longer a constant, but sigma is a function on the equator. So here, this blue circle is the equator of the hemisphere. I'm going to show a little bit clearer picture a little bit later, like with the whole hemisphere. But this is, just the equator of the hemisphere. And in this case, in general, there is no systematic doubling. So we had this systematic doubling for sigma constant. But and that was a feature of separation of variables. But in general, there is no separation of variables. And there is, by the way, I should have mentioned, so the variable sigma case is joined with Alexander Pushnitsky. And I'm going to, of course, when I'm going to state the result, I'm going to mention his name, but maybe I should have mentioned it already here. Anyways, so there is a notion of clusters, and clusters are, so basically if we start from the Neumann energy, these are intervals of width square root of L. Now, here is the question number 3. So here we are going to slightly redefine notation. In the previous slides, sigma was a constant, and we were allowed to vary sigma, and everything was a function of sigma, like lambda j was a function of sigma. Now sigma is a fixed function, and we are going to multiply it by by alpha, and now the variable is alpha. Let's assume there are two different indexes j and k, so that as functions of alpha, the corresponding energies indexed at j and k are equal. What does it say about sigma? Does it imply that sigma is a constant? Okay, and this is an inverse spectral problem. More generally, let's suppose that we take, instead of the sphere, we take any surface, and let's suppose that we encounter two branches that coincide. What does it say about that billiard? I have no idea. Okay, I think it's a nice, but probably very difficult inverse spectral problem. Okay, so with Alexander, we derived a limit distribution that I'm going to define next. There's no separation of variables, no circular equation. We use perturbation theory for operators, and there is no simplicity of spectrum any longer. Okay, so let me just let me now describe the results with Alexander. Okay, so again we have, so let me just repeat, we have clusters. These are just those eigenvalues that lie in energy window of width square root of L. And we consider, so we have this sphere or hemisphere, and we restrict it to hemisphere, and we consider involution on the equator. Phi goes to phi plus pi. Okay, and there are some odd functions with respect to that involution and some even ones. But every function on the equator we can decompose as a sum of odd and even. And it turns out that the limit distribution only depends on the even part. And no matter what is odd part, it has no impact on the answer. And we can therefore assume that sigma equals to sigma even in the first part. That is, in the first place, we can assume that sigma that we started is even. This is not obvious at all, but it turned out from our work. Quite naturally. Okay. Now the theorem is the following. So I'm going to state it in the beginning with a test function, but in fact we're going to derive by change of variable a limit distribution. So
you need to divide by L plus 1?
Yes, you're right. Yes, thank you, sorry. The previous audience did not notice that, or maybe they did. Or maybe they did, but they didn't. But I don't remember. I think I wanted to correct it after they actually probably did, but I forgot to do it. Or maybe I did, but I used the wrong file. Anyways, so this is the result. You can see that. Let's fix a phi. Okay. So I claim that if we fix phi, then whatever distribution we get is consistent with the earlier result with Zev. Okay, but in fact, this is a superposition of those as if sigma is, as if phi is fixed and constant around, and this is a superposition. And this is what we get if we change the variable. So this is the limit distribution, rho of y. I don't expect you to follow everything, but you can see that this is for a given phi. This is the same distribution that we derived with Zev. Now we can see make some observations. So these are indeed the superposition of those distributions for constant sigma. The positive values of sigma push upward the Robin and Neumann gaps, and the negative push them downwards. If sigma is of variable sign, then unlike what Zev and I discovered, the limit distribution is supported on both the positive and the negative sides. And sigma is odd, so everything here is in terms of sigma even. If sigma is odd, then the corresponding distribution converges to delta at 0. And it means that most, not necessarily all, Robin and Neumann gaps are small. It does not mean that they all vanished identically, and it does not mean that a positive proportion vanishes identically, just that they are small, they are converging to 0, and most of them. But it doesn't say anything about all of them. And the question is whether or not we can rescale, in this case, if sigma is odd, the Robin and Neumann gaps so that we get a meaningful result. And somewhat surprisingly, the answer is not always, at least. Okay, so the simple answer we give is no. Why is that? So sigma is an odd function. For example, we can take sigma as an odd trigonometric polynomial on the equator as a function of phi. This is the angular variable. And if it's an odd trigonometric polynomial, then what we proved is that all but big of 1 of the Robin Neumann gaps vanish identically, just simply 0. And the big of 1 is depends on the degree of the polynomial. Effectively, this is pretty much except for at most d, where d is the degree. But it means that there is no way to rescale the Robin Neumann gap so that we get anything meaningful. Because these are just 0, there's nothing to study here. And it turns out that an analogous situation occurs if instead of perturbing our system by adding Robin boundary condition, we add a potential on the whole sphere. So a limit distribution for eigenvalues was derived. That's Weinstein in 1977. It degenerates if V is odd. That is, it converges to a delta at 0. And Guillemin found some distribution after scaling for some select odd potentials V.
Did the rescaling depend on which odd potential?
Yes.
Different potential.
I believe so. Sasha, do you remember? I mean, so first of all, it is only pertaining for some specific ones. Okay, so it's not true that for every V, you can choose any scaling. I don't think they have any explicit result like ours of negative nature. But they have like partial positive result. So to your question, I find it highly unlikely that if it's only for select V, then it would not depend on what is V. But my confession is that I don't remember that very well. Okay, but in general, one would think that it's possible to infer the result on the Robin-Neumann gaps from the result by formally substituting very specific potentials. I'm going to show which ones. So one way to create the Robin-Neumann, the Robin boundary condition seemingly is by taking a potential which is supported on some strip around the equator, which is going to simulate the Robin conditions. But it turned out that, that whatever the limit distribution we get from there is wrong. So it's impossible to, so there is a factor of 2 somewhere. And it's impossible to justify switching of the limits. In this case, this is epsilon that designates the width of the strip. And L, this is the energy to infinity. Epsilon is supposed to vanish. So for, in our case, we first take epsilon to 0 and L to infinity next. And in the classical literature, they first take L to infinity and then epsilon to infinity. The limits do not coincide. Okay, so now I have about 8 minutes to speak about the ingredients of the proof, which is better than my previous attempt. So let me just repeat what we already discussed. The variational formula for the derivative of lambda j, that is the, this is an analytic branch of eigenvalues as a function of sigma. So the derivative equals to the integral on the boundary of the corresponding eigenfunction, save to those bifurcation points. In bifurcation points, there is ambiguity. But these are discrete. And then we can apply the fundamental theorem of the calculus. And then the Robin-Neumann gap is precisely the integral of this derivative of lambda j as a function of sigma. Now, so here, therefore, we need to, if we want the average of the dj of sigma, then by the magic of inverting the order of integration, it amounts to the study of this function. So this is the average of the L2 norms of the functions confined to the boundary, which is this function. And this turns out to coincide for every fixed sigma, turns out to coincide to local while law at the boundary. And I cite, so we cite Ozawa and Hassel-Zerdich. So we have this convergence to this number 2L, twice the length divided by area, which is the theoretical mean that occurs if we assume that the functions are equidistributed. There is a caveat here that there is no uniformity with respect to sigma, and we had to somehow justify how to switch the limit and the integration. Now, the question, the most subtle question is, so that kind of settles the convergence on average in mean. But the question is the corresponding quantum ergodicity, how to infer, how to prove the convergence for density 1. So then there is a quantum ergodicity for boundary values, which states that for every sigma, there is a convergence of these L2 masses to, again, this theoretical mean along the density 1 sequence of J. But there is, so in fact, it's a stronger result. It's not just a convergence of the masses, but this is a convergence as weak star convergence of measures. But the caveat here is that the exceptional sequence, the exceptional thin sequence of J depends on sigma. So therefore, we cannot just substitute this variational formula and just say that for every sigma we have this convergence and therefore we can integrate it. No. I mean, if we do that, then we'll end up with nothing, because for every sigma have a different sequence J, and then we have to excise all of those that correspond to sigma, say between 0 and 1, and like we may end up with nothing. So we somehow resolve that, and that's the main issue here, by some variance, subtle variance computation, and it turned out that it works. Now, why did we discuss that that the disk billiard is a natural example for the bounded Robin-Neumann gaps? So let's first show how to show the upper bound. Again, we apply the variational formula. And by the variation formula, we have that the integral, that the Robin-Neumann gap is the integral of the derivative. That's the fundamental theorem of the calculus. And there is a result that in general, there is an upper bound for the L2 mass at the boundary of J to 1/3. But so this bound is saturated for the disk. And for the disk, it is saturated by the so-called whispering Galilean mode, which is these two pictures here. Most of the L2 mass of the function is concentrated around the boundary. And therefore, the corresponding derivative, d lambda j over d sigma, grows like lambda to 1/3. But even from that, we were not able to infer that the Robin-Neumann gaps are unbounded, because the possible bifurcation where two curves can intersect, and therefore it kind of dismisses all the big progress that we made in the Robin-Neumann gap. I would love to see somebody prove that statement. Okay, and surprise, surprise, I got to the very last slide. Okay, and I'm going to discuss how to use the while asymptotics, or precise version of while asymptotics, in order to get non-trivial bounds. So we claim that for the disk billiard, we can get a slightly better bound than the general bound of J to the power 1/3. Okay, so in general, there is two-term asymptotics for the while law. Lambda j is j times an explicit constant. The next term is square root of j, and it is the same one for both the Neumann case and the Robin case. So whenever we are going to discuss, compute the Robin-Neumann gap, both the leading term and the next term are going to cancel out. And the main question is about this error term j to the power theta. What is theta? So it was proven by Kuznetsov, Fedosov, and Colin-Deverdier that for the particular case of this billiard, we can take theta to be equal to 1/3. And for 1/3, theta equals to 1/3, this was not worth this whole discussion because it matches the general bound. Okay, but in fact, Guo, Wang, and Wang proved that we can take for this particular billiard theta to be equal slightly smaller than 1/3, and that improves the general upper bound. And the slightly smaller is 1/990. So in order to prove that, we need to appeal to an exotic lattice point counting problem in an exotic region. This region is what is depicted in this picture. This is an explicit function. And there is no way to get an improvement of beyond 2/7, because 2/7 is the precision with which Kuznetsov-Fedosov approximated the number of eigenvalues by the number of lattice points in this exotic region. So it is quite plausible that you can improve the 2/7 for the lattice point counting problem, but that will not improve the corresponding while law or bound for the Robin and Neumann gaps. So that was my last slide. I think that's the first time maybe ever that I finished the whole presentation.
Okay, thank you. Any comments? Yes.
Yes. Can you use this whispering gallery observation for non-circular shapes, like to get estimates for this like whispering gallery models exist for?
For which purpose? To show unboundedness of Robin Neumann gaps. I mean, I wish. It is quite plausible that you can use, but it does not sound that this is easier than to do it for the disk billiard. So if we cannot, and by the way, when I say I cannot do it, it doesn't mean that you cannot do it. I only say that, like, I found it difficult because of the intersection with other curves. But I find it unlikely that, I don't want to say you, but somebody would do something that is not the disk without doing the disk. But I don't find it extremely unlikely that somebody will do the disk and a non-disk.
So the main obstacle is the crossing.
Yep.
Right, the bifurcation.
Yeah, we can prove a weaker statement for the disk. We can prove that there are Rn scars for the disk, which is a weaker statement than unboundedness. Even that is not so trivial, in my opinion. It was never published, and this is one source of. This is one program how to prove Rn scars for the stadium. But to prove that this is unbounded, I don't know how to do it. And again, it is quite plausible that somebody would prove it. I do not say it's impossible. And I think that the result is correct.
So here at the Newton Institute, we used vast computational resources. And I think I'm using the royal we.
I've done about a million of them.
What's the biggest?
80?
About log
80.
6 log n.
He's in third place. Up to 1 million, I think the maximum we found was 80.
Yeah. There.
It's quite interesting. I would like to see it.
You can fit 80 versus 1 million.
Yeah.
The picture that I showed, we had like 2,000. It went until about 30.
6 log n is a good approximation for the max.
It's quite interesting. What I would expect before you said whatever you said, what I would think that it grows like a power. But if you show it numerics, I'm happy to concede. I was thinking about, okay. I find it unlikely. No, look. This is a statement. This is a statement about Bessel zeros. Basically, what we need to find is whispering gallery mode, which is sufficiently with growing distance to the next eigenvalue.
Let me disagree. It's not a statement about Bessel zeros. It's a statement between different branches
Yes.
and intersection.
Absolutely, yes. That's what I meant. That's what I meant by Bessel. But these are branches of Bessels. It's not a single Bessel. But it's a statement if you basically, what we need to find is a zero of a Bessel that corresponds to a large derivative, for example, a whispering gallery mode or something close to that, so that the zero itself is sufficiently, like with growing distance, to the next branch, which is growing slower. I would think that, I mean, it has to be a big conspiration of the nature against us so that it will not happen. But nature already, you know, I've seen weirder things in the world, but this particular one, I would think that it's unbounded.
Oh, question? Yeah.
For convex sets in the Euclidean space, do you have some particular general behavior? Or?
No, I mean, convex sets might be, so, okay. If you speak about convex chaotic sets.
No, they can.
Convex sets in Rn. Convex sets. Convex.
I mean, stadium is convex, no?
General
Higher dimension.
in 2 or higher dimensions, if there is something particular concrete, I have an exact question. Is it D2 greater than D1 for bounded open convex sets of R and R2?
So I don't know something is asking
If the cap
first
it is
Robin
smaller-
less
I don't know. I know. I mean, I can figure out. Okay, I don't know the answer, and I would think that the answer is no.
than formulate
I would think that the answer is no.
If we go back to, can you show the slide with the full?
Yes.
Since you're asking the first and second.
Yes. But for convex sets only.
You switch the two.
But all of them. I mean, maybe I'm okay. 3 of them are convex, no?
Let's all continue. There you go.
I mean, 3 of them are convex, right? Okay, this is so here D2 is bigger than D1. Okay, here D2 is bigger. Here I cannot tell.
Okay. So for the mushroom, it looks like.
But mushroom is not convex.
It's a fair question.
The question, my question is for convex only.
Okay, I will prove your question. We will disprove this D2 always bigger than D1. Regardless of this. I know why I asked this. Okay, perfect. We end exactly on time. I wish I could say that I've been waiting for. I would be lying if I said that.
The cognate